Hi guys, welcome to Prison Raw. And today we're gonna be looking at a question under static electricity physics. Yeah. So the question says an electric field E, which is 100,000 newtons per coulomb moving in the x direction, causes a 5 gram point charge to hang at a 20 degrees angle. What is the charge on the ball? So I'm sure you can see here this is the 5 gram ball, and then we have an electric field. Let me just draw it for you guys for you to see it. An electric field moving in the x direction. So what this electric field does is it causes this ball to hang at an angle of 20 degrees, as you've seen there. All right. So, and I'm sure you understand that the electric field has a force. That's why it was able to push the ball, which is charged, of course. And the equation which connects the electric field to the force being applied is simply the force is equal to the charge of the ball that's being pushed by electric field multiplied by the electric field itself. So here we can say that the electric field exerted a force of the charge of the ball multiplied by the electric field itself. Okay, now we see that since the ball is hanging, this right here is a string. Okay, this right here is a string, and whenever you see string, that means there is tension. Okay, so that string has tension. Now this tension has components because it is not exactly in the x and it is not exactly in the y, but it is in both. That means it has a component in the y and a component in the x. So the y component is, let me draw it for you guys there. This is the y component of the tension, and the y component, you can see that it's on the adjacent side, so it is tension cosine theta. All right, and we also have the x component of the tension. Let me draw it for you guys as well. There it is, and you can see that it is opposite to the angle, therefore it is t sine theta. Okay, now we also understand that this charged ball has mass. So if it has mass, that means it has weight. All right, so let me just draw the weight. So the weight, it always acts vertically downwards. So this is the weight of the ball, mg. Okay, I think we've labeled everything that needs to be labeled. It's more like a free body diagram. So let me simplify for you guys. So we have the charged ball, and we have the electric force moving in that direction, okay, which is the charge of the same ball multiplied by the electric field, and opposite in that direction we have the tension, the x component of the tension, t sine theta. Okay, and you can see why it is balanced there, because we have one force acting towards the right and one force acting towards the left, so they more like cancel out. And apart from that, we also have the y component of the tension acting upwards, which is t cosine theta, and we also have the weight of the ball acting vertically downwards. So you see we have one force up and one force down, so they both cancel out, hence the ball is in what we call equilibrium. All right, so let me just write equations to illustrate what I'm talking about. So we can say the summation of forces in the x will be equal to this force, which is acting in the positive x direction, minus this force, the x component of the tension, which is acting in the negative x direction. And since the ball is in equilibrium, these forces sum up to 0. And in the y as well, summation of forces in the y will be equal to t cosine theta, which is acting in the positive y direction, minus mg, which is acting in the negative y direction, and these forces sum up to 0. Right, so from the equation, the first equation here, which is in the x, we can get the formula. The tension, therefore, in the x direction has to be equal to the electric force that is also acting in the x direction, so that once we add those two, since they're in different directions, they sum up to 0. And it makes sense because if you look at this diagram here, for the ball to be in equilibrium in the x, this force there has to be equal to that force for it to be balanced. Otherwise, if one force was greater than the other, then there would be motion in the direction of the greater force. Okay, so we can say this is our equation 1. Then from equation 2, likewise, we can say that's t cosine theta is equal to mg, and this is our equation 2. And I'm sure you can see why as well, because if this thing has to be equal in the y direction, then the tension acting in the y direction upwards must be equal to the weight which is acting downwards for it to be balanced. Otherwise, if one force was greater than the other, then there will be motion in the direction of the greater force. Okay, so remember, we are trying to find the charge of this ball right here. So how can we find it from here? How about we make tension the subject of the formula in the equation 1, then replace that value in equation 2. I think that sounds like a good idea. Let's do that. So from equation 1, we see that tension is equal to the electric force divided by sine theta. Okay, so replacing tension in equation 2 there, we'll have the electric force divided by sine theta multiplied by cosine theta is equal to the weight of the ball. Okay, so let's make the charge the subject of the formula, because that's what we're trying to find. Okay, so from here we can divide both sides by cosine theta. So cosine theta there and cosine theta there, so that will cancel over there, and we have the electric force divided by sine theta is equal to the weight of the ball divided by cosine theta. Okay, then we can multiply both sides by sine theta. So that sine theta and that sine theta can cancel, and we'll have the electric force will be equal to, let's write this side like sine theta divided by cosine theta multiplied by the weight. Then we can divide both sides by E, which is the electric field, so that we have now Q as the subject of the formula, which is the charge of the ball, and that's what we're looking for. But then again, you know that sine theta divided by cosine theta is just simply tan theta. So we have tan theta multiplied by mg divided by E. Okay, and this formula right here will help us find the charge of the ball. Okay, so we know that and theta is just 20 degrees. Remember from our diagram, our theta there is 20 degrees multiplied by the mass of the ball. And remember, the mass has to be in kilograms, and we were given 5 grams. So 5 grams, for it to be in kilograms, you just have to divide it by 1,000, and we'll have 0.005 kilograms multiplied by gravity, acceleration due to gravity. That's meters per second squared. Okay, 9.8 meters per second squared. Then divided by the electric field, which was 100,000, if I'm not mistaken. Yeah, there, 100,000 newtons per coulomb. Punching this into our calculator, we get make sure your calculator is in degrees because we're using 20 degrees there. Okay, and we get that the charge of the ball is 1.78 times 10 raised to the power -7 coulombs. And that right there is the charge of the ball. Okay, so the question is, how do we determine the sign? Okay, that's very important, because of course we know that the magnitude of the charge is this 1.78 times 10 to the power -7 coulombs. But is it positive or is it negative? And how do we determine that? So there's one thing you should know about positive charges, is that positive charges produce an electric field that moves away from the charge. Okay, that's how they behave. But for negative charges, it is the opposite thing. For negative charges, they produce an electric field that moves towards them. Like that. So now, let's go back to the diagram here. Let me use another color. Here. So, how I like to think of it is like, since the electric field was moving in that direction, it could be that it was coming from a positive charge. Let me just do it like that. Then it was going in that direction. Or it could be that it was going towards a negative charge, hence moving in that direction. But let's say if it was coming from a positive charge, then this ball moved away from that positive charge. That means this ball could actually also be positively charged because it was being repelled. Remember, like charges repel, but opposite charges attract. Okay, so if this side was positive, if this side was positive, then the ball moved away from that side. That means the ball was positive, which is true also for this other side as well. Because think of it like this: the electric field was moving towards a negative charge, or a negative charges, we don't know. Okay, but then it moved towards those negative charges. That means it had to be positive. Okay, that means from both sides, either side, the assumption still remains true. The ball had to be positively charged for it to be repelled by these positive charges on the left, and for it to be attracted by these negative charges on the right. So back to our answer, we say that the charge on the ball is positive. Okay, thank you guys for watching my video. Please make sure you like, subscribe, and turn on the notification bell so that you get updated whenever I post any new video. Otherwise, thank you for watching. This was Reason Realm, and see you in the next video.